What if the universe started building complex structures far earlier than science ever predicted? Not gradually, not slowly, but fast. Shockingly fast. What if galaxies didn't patiently wait billions of years to grow up, but instead appeared too early, too massive, and too organized for the story we thought we understood? Because that's exactly what scientists are staring at right now. Deep in the darkness of space, NASA's most powerful telescope has been quietly sending back images that weren't supposed to look like this. Images that don't scream chaos. Images that don't look young. Images that feel mature, calm, almost confident. And at first, researchers thought it had to be a mistake, a glitch, a calibration error, something misread. But the data kept coming, again and again and again. What they saw didn't break the laws of physics, but it pressed uncomfortably hard against the edges of what our best theories said should be possible. Structures showing up when the universe was still supposed to be figuring itself out. Systems that looked like they had time when time was the one thing they shouldn't have had. Too early, too bright, too organized. For decades, scientists believed they understood the universe's timeline, a violent beginning, a long, messy childhood. Then, slowly, order emerges from chaos. That story worked. It explained what we saw. Until now, because these new observations don't fit neatly into that timeline. They don't scream impossible, but they whisper something far more unsettling, incomplete. And that's where the tension begins, not with aliens, not with secret cover-ups, but with a much quieter, more fascinating idea that the universe may have grown up faster than we ever imagined. Right now, teams across the world are rechecking models, rerunning simulations, asking uncomfortable questions, not because science failed, but because it's doing exactly what it's supposed to do when reality pushes back. And if you enjoy stories like this, where real discoveries challenge what we think we know, make sure you're subscribed to Evolvex. It really helps the channel grow, and if you find this fascinating, a like and share goes a long way. Because this isn't just about distant galaxies, it's about a universe that may be far more efficient, far more mysterious, and far more surprising than we ever gave it credit for, and we're only just beginning to see it. What science expected. For decades, scientists had a clear, simple story for how the universe grew up. It began with the Big Bang, an event so violent and energetic that everything was thrown into motion at once. The early universe was like a massive construction site after an explosion, hot, chaotic, and filled with raw material, but no finished structures. According to this picture, nothing neat or organized should appear early on. Order was supposed to take time, patience, and countless small steps. In this old story, the first galaxies were expected to be small, faint, and messy. Imagine trying to build a city while thick fog covers everything and the ground itself keeps shifting. Gravity slowly pulled matter together, but progress was slow. Galaxies needed billions of years to settle into recognizable shapes. Any large, bright, or well-organized system was supposed to be a late arrival, showing up only after the universe had plenty of time to calm down. Holding all of this together was what scientists often describe as cosmic scaffolding. Dark matter provided the invisible framework, while gravity did the heavy lifting, slowly guiding gas and dust into stars and galaxies. This model, known as lambda cold dark matter, explained an enormous amount of what astronomers observed for years. It matched simulations, observations, and measurements with impressive accuracy, and for a long time, there was no real reason to doubt it. A new set of eyes. When the James Webb Space Telescope was launched, it carried enormous expectations. This was not just another space telescope, but a new set of eyes designed to see the universe in a way no instrument ever had before. Scientists were optimistic. Webb was built to confirm long-standing theories, to fill in missing details, and to sharpen the picture we already thought we understood. Few expected it to challenge that picture itself. What makes Webb different is how it sees. Instead of focusing mainly on visible light, it observes the universe in infrared. This allows it to look through thick clouds of cosmic dust that block older telescopes, revealing regions where stars and galaxies are born. Infrared light also stretches as the universe expands, meaning the oldest and most distant objects shine most clearly at these wavelengths. Webb was designed specifically to capture that ancient light. Looking far into space is also looking back in time. Light takes time to travel, and the faint glow from the earliest galaxies has been moving toward us for billions of years. When Webb detects that light, it is not seeing those objects as they are now, but as they were when the universe was extremely young. This turns the telescope into a time machine, capable of peering closer to the universe's beginnings than ever before. At first, everything felt exciting and reassuring. The images were stunning, the data was rich, but as scientists began to look closer, curiosity slowly gave way to confusion. Some of what Webb was seeing looked familiar, some of it did not, and that was the moment when quiet questions started to form. Galaxies that are too mature. Then came the moment that truly caught everyone off guard. As data from the James Webb Space Telescope poured in, astronomers began identifying galaxies in the early universe that did not look small, faint, or chaotic. Instead, they appeared massive, intensely bright, and surprisingly structured. These were not rough drafts of galaxies. They looked more like systems that had already gone through long periods of growth and organization, even though the universe itself was still very young. This was unexpected because, according to existing models, there simply should not have been enough time. The early universe was only a few 100 million years old when some of these galaxies already appeared fully developed. There should not have been enough raw material pulled together by gravity, nor enough time for stars to form in such large numbers. Everything about them seemed to say too early, not impossible, but earlier than models had predicted. The reaction from scientists was immediate but careful. Surprise came first, followed closely by cautious excitement. Teams double-checked distances, reanalyzed brightness measurements, and compared results across different instruments. No one wanted to jump to conclusions. Extraordinary claims demand extraordinary verification, and the first instinct was not to rewrite theories, but to make sure the observations were real. As more independent studies confirmed the findings, the tension only grew. The universe was doing something unexpected, not by breaking the rules, but by revealing that the timeline itself might be off. These galaxies were not wrong. Our expectations might have been, and the phrase that kept coming up again and again was simple and unsettling: too early. Spirals in the early universe. Among the most unsettling discoveries was something astronomers never expected to see so early at all: spiral structure. Spiral galaxies are not random shapes. Their sweeping arms require stability, balance, and time. Stars must orbit in an organized way, guided by a steady gravitational rhythm that can only emerge after long periods of settling. In the old picture of the universe, this level of order was supposed to be a late achievement, not an early one. That is why spotting galaxies with spiral features in the early universe was so shocking. These systems appeared when the cosmos was still young, when frequent collisions and turbulence were expected to dominate. Spiral arms should have been torn apart before they ever had a chance to form. Seeing them so early suggested that some galaxies reached a calm, balanced state far faster than anyone had predicted. Once again, the same quiet phrase echoed through the data: too early. The implications were subtle but profound. If spiral galaxies could emerge this soon, then matter must have settled more efficiently than models assumed. Gas cooled faster, stars formed sooner, gravitational systems stabilized earlier. This did not mean that physics was wrong. Gravity still behaved as expected, and the laws governing motion still applied. What appeared to be shifting was the pace of cosmic evolution, not its rules. Psychologically, this changes how we imagine the early universe. Instead of a long, chaotic struggle toward order, it begins to look more capable, more efficient, and more structured than we once believed. The universe may not have stumbled its way into complexity. It may have reached it with surprising speed, and that realization makes everything that comes next feel even more uncertain. Black holes that grew too fast. Another piece of the puzzle made the mystery even harder to ignore. Alongside these early galaxies, astronomers began finding signs of supermassive black holes already in place when the universe was still very young. These were not small objects quietly growing in the background. They were enormous, millions to billions of times more massive than the Sun, actively pulling in matter and shining brightly from the centers of their host galaxies. According to older expectations, objects like this simply should not have existed so soon. For a long time, the assumption was that black holes grew slowly, A small black hole would form from the collapse of a massive star, then gradually gain mass by feeding on nearby gas and stars. This process was thought to take billions of years, limited by how much material a black hole could consume without blowing its surroundings away. Under that picture, the early universe did not seem old enough to produce the giants now being observed. New observations have forced scientists to rethink that timeline. Instead of steady, gentle growth, early black holes may have gone through intense feeding phases, surrounded by dense clouds of gas in young galaxies. New observations have forced scientists to rethink that timeline. Instead of steady, gentle growth, early black holes may have gone through intense feeding phases, surrounded by dense clouds of gas in young galaxies. In such environments, black holes could grow far more rapidly than once assumed, not by breaking the laws of physics, but by operating at the extreme edges of what those laws allow. The idea is not that black holes behaved impossibly, but that the early universe provided conditions far more favorable for fast growth. Even so, the question remains deeply unsettling. When astronomers look at these ancient objects, they are forced to confront a simple mystery. How did something so massive appear so quickly? The answer is still unfolding, and it lies somewhere between revised models, better data, and a universe that continues to surprise the people trying hardest to understand it. Dark matter. Behind every galaxy, every spiral arm, and every early structure lies something no one has ever seen directly. Dark matter. It does not emit light, absorb it, or reflect it, yet its gravity shapes the universe on the largest scales. In the standard picture, dark matter acts like an invisible framework, gathering first and pulling ordinary matter along with it. Without this hidden mass, galaxies would never have formed the way they did. This idea has explained decades of observations with remarkable success. The behavior of dark matter matters deeply for the timing of cosmic structures. In existing models, dark matter is described as cold, meaning it moves slowly and clumps efficiently. These clumps become the seeds around which gas collects, stars ignite, and galaxies grow. If dark matter behaves exactly this way, structure formation follows a relatively predictable pace. But when Webb began revealing galaxies that looked mature far earlier than expected, scientists had to ask whether those initial assumptions were too simple. This has led to careful new considerations. Some researchers are exploring whether dark matter in the early universe might not have been perfectly cold, or whether its behavior changed slightly over time. Even small differences in how dark matter moves or interacts could speed up the formation of early structures without violating known physics. These ideas are not radical departures, but refinements, subtle shifts tested through simulations and observations rather than speculation. It is important to be clear about what this does and does not mean. Dark matter has not been disproven, and the core framework that includes it remains strongly supported by evidence. What is happening now is something far more characteristic of real science: humility in the face of new data. As observations improve, models are adjusted, not discarded. Dark matter remains invisible, mysterious, and essential, but the universe may be revealing that it behaved in more nuanced ways during its earliest moments. And that uncertainty is not a weakness. It is the engine that drives discovery forward. The bigger problem. As more data came in, a pattern began to emerge that was hard to ignore. Galaxies were forming earlier, spirals were organizing faster, and black holes were growing at a rate that old models could barely accommodate. Across different observations, the message was consistent. Everything seemed to be happening faster than predicted. The universe was not waiting its appointed time. It was moving ahead on a schedule that challenged our expectations. This tension is not limited to galaxy formation alone. Another persistent puzzle in cosmology, known as the Hubble tension, has also raised questions about timelines. Measurements of the universe's expansion rate in the nearby cosmos differ from those inferred from the early universe, suggesting that our understanding of cosmic time and growth may be incomplete. While not directly caused by early galaxy formation, this discrepancy reinforces the idea that the universe's pace is more complicated than previously thought. Taken together, these independent problems point toward a single, unsettling possibility. The universe may have grown up faster than expected. It is as if cosmic processes accelerated, building structure, forming massive galaxies, and feeding black holes in record time. Nothing here violates the laws of physics, but the sequence and speed of events may not align with our prior assumptions. Scientists are left to ask, have we underestimated the efficiency of the early universe? Or is there something else, something subtle, driving these timelines? What scientists are actually doing now? Right now, scientists are taking a methodical approach to make sense of these surprising findings. They are not jumping to conclusions or rewriting physics overnight. Instead, teams around the world are adjusting cosmological simulations to account for galaxies appearing earlier and more structured than expected. By tweaking the parameters that govern how gas cools, how stars form, and how matter clumps together, researchers can test whether these accelerated timelines can naturally arise within the laws we already know. Alongside simulations, astronomers are refining models of star formation efficiency. Early galaxies may have converted gas into stars more quickly than previously assumed, and understanding the precise rate at which this happens is key to explaining their unexpected brightness and mass. Researchers are also testing black hole growth models, exploring scenarios where supermassive black holes could feed rapidly under dense early universe conditions without violating physics. Each adjustment is carefully checked against observational data to ensure that models remain consistent and predictive. At the same time, telescopes like the James Webb Space Telescope continue to gather more data, providing higher resolution images and spectra of distant galaxies and black holes. Every new observation is cross-verified, and multiple teams independently analyze the data to confirm findings. This process of careful verification and incremental refinement is a hallmark of real science, emphasizing caution and rigor over sensational conclusions. Scientists are building a clearer picture step by step, understanding that mysteries of the early universe are solved not by leaps of imagination, but by patient, careful work guided by evidence. As we look back at all these discoveries, the early massive galaxies, the spirals that appeared far sooner than expected, the supermassive black holes that grew at lightning speed, and the subtle complexities of dark matter, a clear picture emerges. Science itself is not wrong. It is evolving. Each new observation challenges our assumptions, yes, but it also deepens our understanding. The universe is not broken. It has always been operating according to the laws of physics. What is changing is the story we tell about its timeline, its efficiency, and its capacity for surprises. These revelations remind us that knowledge is never final. Every telescope, every simulation, every careful measurement peels back another layer, revealing more nuance, more subtlety, and more questions. The cosmos is proving to be faster, more organized, and more intricate than we imagined. That is not a failure of science. It is a testament to its strength. With every discovery, we refine our models, adjust our theories, and build a more accurate understanding of the universe. And yet, the most exciting part is the unknown. What else is waiting, just beyond what we thought was possible? What hidden structures, unseen forces, or surprising timelines are still out there, quietly shaping the cosmos? Each revelation opens doors to questions we could not have imagined a decade ago, and each answer sparks new curiosity, driving exploration forward. If this journey through the universe has sparked your curiosity, there's more to explore. Like this video, comment below with your favorite cosmic mind-blower, share it with friends who love space, and make sure to subscribe to Evolvex for more stories that push the boundaries of what we know. The universe is vast, mysterious, and awe-inspiring, and together we get to witness it as it unfolds. So keep looking up, keep asking questions, and never stop wondering what's just beyond our reach.